These small ampules here can emit light for over 25 years without an external power source. This is because they contain a radioactive element, tritium. Tritium is an isotope of hydrogen containing 2 extra neutrons and undergoes a beta decay to form helium-3. The beta radiation is easily shielded by the glass walls of the ampule. Nevertheless, in many countries there are regulations limiting the amount of tritium in such a vial to 1 gigabecquerel, which is around 2.6 micrograms. In today's video, I will be visiting a lab that is authorized to work with 40 grams of tritium, which is 14 million times the amount in such an ampule. So join me in my visit to the Tritium laboratory at the Karlsruhe Institute of Technology. Before we enter the main laboratory, let's look at a method to determine the leftover radiation in contaminated objects, such as decommissioned equipment. When talking about tritium, this poses a real challenge because tritium, just like hydrogen, can penetrate deep into different materials, even metals. And since even a very thin layer of material blocks the beta radiation, it cannot be measured with a detector held to the surface. A quick remark before we enter the lab. The Tritium laboratory maintains strict monitoring for surface contamination to ensure a safe and controlled environment. In fact, the cleanliness standards are so high that visitors can enter the lab without the need for additional monitoring devices.
This is where we have our calorimeters. Essentially, if you have tritium in some most often waste, it's difficult to measure because if you can't take the activity of the surface, you need to still somehow quantify how much tritium is in a given piece of material. We do this with calorimetry. So we measure how much heat is produced in the radioactive decay to find out what the activity in that piece of material is.
And you can't measure the radioactivity directly because the beta decay is so weak that you can't measure it on the surface. That's the problem.
You can't measure it on the surface. You can at most, even if you go via X-rays, you can only at most measure the first few microns if you're lucky in material choice. But if you have, like, for example, a big metal vessel of some kind or an old valve that's out of commission, you can't really get in there and find out how much activity is stuck in there. But if you can just put it in a container, and no matter what will happen, the energy of the decay will at some point be turned into heat. The energy is so low that nothing can escape out like you would have with gamma decays. So all of that decay energy is transformed into heat, and we can measure that with the calorimeters. It's not the most sensitive measurement, but it's the most kind of all-encompassing. You're sure that the activity is what you measure there.
But the temperature you have to measure must be tiny, right? I mean...
Yes, I mean, you see the kind of dynamic ranges in terms of watt powers that you can see.
Yeah.
So it's a few microwatts at best. But that means in quantifiable terms, we can see something on the microgram scale with the calorimeters. For just radiological safety, for things you would touch, that's not really an amount of tritium you would want to get in contact with, but if it's for disposal of used material,
yeah,
that's important to know what kind of activities we give off to the disposal sites. Do you want to have a look at it?
Oh yeah, sure.
We have several of these calorimeters, bigger ones, smaller ones.
So it's basically an insulated container?
Yeah.
You put your sample in there, close it off, and then you measure the temperature increase?
You heat it up to a certain, with a certain power.
Yeah.
And then you put your sample in and see by how much that power decreases that you need to get to the same temperature. Measure the temperatures you need to keep this entire inset stable, and then you put your sample inside. That way you always have the same defined thermal connection.
So is the container we're seeing back there, is it this one or the outer one?
We have these cans standing here.
Ah, okay.
Ones
yeah.
with the nice radioactive labels.
Yeah.
Not very exciting on the inside. Basically you take this entire thing,
yeah,
and put it through the lid at the top into this calorimeter
okay,
cup.
I see. Yeah.
So you always have kind of a defined geometry,
yeah,
and a defined heat flux. So you know how much heat input from a wire means how much additional heat do you have in from the radioactive decay inside. Basically, you have a steady state, you have nothing radioactive in it.
Yeah.
You say, I'll put it to just a number out of the blue, 40 degrees centigrade.
Yeah.
It's easy because it's above room temperature, so you're less affected by fluctuations. And then you put, you know, to get 40 degrees centigrade, I need 1 watt of power.
Yeah.
Then I put in my radioactive sample and see if I still want to keep the temperature stable. My power draw now is only
0.9 or something.
0.9.
Yeah.
So I know that the sample I put inside has 0.1 watts of thermal power. And then I can calculate that with the decay heat to how much tritium is inside.
Let's talk about how they monitor whether or not tritium has been released inside the laboratory. As we've already discussed, simply placing a detector on, for example, the wall won't be sufficient because even the casing of the detector itself would block the radiation. For that reason, all of the labs are equipped with ionization chambers that continuously monitor the room's atmosphere.
These are the, in this case, it's the atmospheric ionization chamber. You can see if you follow the lines, it just sucks in air and passes it on the one hand through the ionization chamber, where if you have tritium decays or any other decays, it will produce a signal, which it then calculates to what is that equivalent in activity in the atmosphere in the room. And afterwards, it also passes it through this bubbler bottle.
The purpose of this step is to condense tritiated water in the gas washing bottle. At regular intervals, the water is subjected to a highly sensitive scintillation measurement.
And that way you can collect it in the water and then later test the water as well to get a kind of integral measurement of how much was in the room atmosphere. That just is kind of 2 stages of safety. One is the immediate. If a puff of tritium would get into the air, you would see it immediately.
Yeah.
This one is an integral measure, but being integral, it's more sensitive because you can collect activity over time.
And the ionization chamber is basically 2 metal plates with a potential difference. And if there's a radioactive decay, you can measure a...
Yeah, basically you have one cathode, one anode. You put a high voltage between them. If you get a radioactive decay, you produce some free charges inside. And by that potential difference, those are accelerated, usually form some kind of cascade of charged particles, and you can measure a tiny blip in the current.
With that out of the way, let's finally enter the main laboratory and see how they work with tritium.
So this now is our lab proper. As you can see and hear, the doors also have a little bit more under pressure as we go from outside to inside. We always have decreasing air pressure just so any tritium leakage will not easily go outside but will rather be contained inside. We are one of the world's only facilities for civilian research which has the license to handle large amounts, in our case 40 grams of the radioactive hydrogen isotope tritium. And we can safely handle these amounts of tritium by enclosing them in glove boxes. In this case, you see one that's not in operation yet, but later on I can show you ones where you can see how they look fully instrumented to safely enclose the tritium, that any operator, such as a scientist like me, is not endangered by the radioactive tritium. In this case, this is our new experiment under construction, the TARP-2 experiment, where we want to do IR spectroscopy on the radioactive hydrogen isotope tritium. To do that, we need to really increase the density, because tritium as hydrogen is only IR active when you have either high pressures or in general high densities. Otherwise, you can't see it in IR. So in order to achieve that, we are cooling down the gas in order to liquefy or even solidify it. Hydrogen, deuterium, tritium are all symmetric molecules. So in first order, they should not be IR active. You should not be able to see them in infrared. But if you increase the density more and more, you get collisions of the molecules. And the collisions allow you to basically have some tiny multipole moments of these molecules, which then allow them to break that symmetry and absorb IR radiation. So you see intensity that varies with density. This is what you can also hear in the background as a cryocooler to cool down to cryogenic temperatures of around 10 Kelvin. All of this piping you can see inside is all kinds of different gas handling. For example, from the top we have different gas supplies coming in. We have hydrogen, deuterium, nitrogen, neon and helium that we want to use.
What are those cylinders? Are they drying cylinders?
Those are filter cartridges that are specific for the gas you want to push through them. They absorb all kinds of other things that are unwanted, such as hydrocarbons or other gases, for example. The ones for hydrogen, I think, also filter out nitrogen, just so you get a really pure gas out at the end. That is really what you want to measure. From there, we can get it into our system, where we have a kind of loop where one side goes through the cell. Then we have a second part inside the cryostat that you can currently not see, but it's a catalyst in order to convert the hydrogen or tritium isomers. Basically, hydrogen has two configurations of the nuclear spin of the atoms in the molecule, parallel and antiparallel. And depending on temperature, you have different ratios of how much of each you have. But if you just naturally put hydrogen at a certain temperature and wait, it's really slow to do this conversion. This is also a problem with hydrogen storage for power applications. Basically, you have hydrogen, you liquefy it, cool it down, but the configuration at room temperature is 75% of something called auto and 25% of para configuration of hydrogen. If you cool it down, the desired equilibrium is basically entirely para. The main issue is this conversion from auto to para releases energy. So you have a process that once you cool it down, slowly on the time scale of days or weeks, releases heat into your system and warms up your cryogenically liquefied hydrogen, which is of course not really desirable. So that's one thing we're looking at with this catalyst, basically, that accelerates this reaction, so you can also already get in production the equilibrated isomer state of your hydrogen, and it doesn't boil off afterwards.
So basically, you're trying to convert it into the power hydrogen before you liquefy it, so it doesn't release heat after it was liquefied.
That is what you would want to do in a power application later on. We're doing this because we want to investigate the different properties that auto and para have, because they have slightly different spectroscopic properties and different thermodynamic properties. For example, they have different speeds of sound.
Interesting, really.
Or heat capacities.
But wouldn't they have to have different densities to have different speeds of sound?
They also have different densities.
Really?
They have different vapor pressures. So you can actually, basically thermodynamically, you can produce everything from pure para hydrogen to 75% auto, 25% para. But you can actually, due to these properties, distill off the auto hydrogen and make pure auto hydrogen if you really want to get. It's a tiny difference, but it's enough to be feasible to do that distillation. It's not useful for practical applications, but for scientific ones, you can do that.
And this is basically also a glove box, but it's not ready yet, right?
Yeah, it's not ready yet. There's no windows in yet, no gloves. We already have the lids to cover the gloves when they're not used. But it's just working in a glove box is always a lot more strenuous than working just without having anything in between you and the entire experiment. So you want to build it as finished as as you can, which most of the time is you just build the finished system and then close the glove box. You can run it with tritium. Then if you're finished, you can slowly take it apart. The taking it apart part usually means you will release some tritium into that glove box atmosphere, because opening a vacuum connection without breaking vacuum, I would be very enthusiastic if somebody built that type of connection, but sadly not available yet. touch.
So basically, is grease from your fingers a problem?
For the glove box interior, not.
Okay.
Right. Because we don't, as you have it in medicine or pharmaceutical science, the glove boxes are not there to protect our product, they're there to protect us. Right. So everything that we put inside that would be like a smudge of a finger, it's not good for a vacuum system, but it doesn't really matter from the radiological perspective. Right. And you want to avoid it where you can, so we do try to clean them as well, but they don't need to be clinically sterile.
And even though this glove box is not ready yet, you already said that there is something going on inside here, right? We can also hear a cryopump running?
Yes, you can hear the cryopump chirping, which is mostly the chirping is the lines actually, just the helium getting pushed through at high pressure.
Ah, okay.
But what you can see, we can go around to the other side. What you can see here is basically an optical window. Yeah. Inside this cryostat is a cell, a gas cell, with two windows. Yeah. So you can look through the entire apparatus. Yeah. And we can fill that with gas from the outside and heat it up to a desired temperature so we can produce different vapor pressures and densities inside. And then what we want to do later is use this IR spectrometer, basically shoot IR light through here and see the absorption lines in the spectrum of hydrogen, deuterium, mixtures of that, tritium.
And that temperature is achieved by the cryopump inside.
Yeah, that is basically, this is a cold head that gets the helium pumped through these lines. And at the very front, you have the cold stage of this cold head that's cooled down to several kelvins. Since we have an optical window, we do have some heat load on it, so we don't quite reach the 4 Kelvin mark.
You mean heat load by basic radiative heat?
Yes.
Oh. Yeah, sure, it makes a difference at 4 Kelvin or something.
At 4 Kelvin, everything starts to look very hot. So if you look in from atmospheric temperatures, room temperature.
What you are seeing here is hydrogen condensing in the cell shown earlier. Hydrogen is used to test the experimental setup before eventually tritium or a mix of tritium and hydrogen will be condensed here. At a certain point, the hydrogen even begins to freeze. If the temperature drops too quickly, it forms a sort of snow, as you can see in the video. For the upcoming experiment, however, it will be cooled down a lot slower, so the solid hydrogen remains transparent and can be used for IR spectroscopy. Next, we will take a look at an operational glove box, learn about the very interesting material requirements to work with tritium, and talk about how they get rid of the tritium that has been released inside the glove box. So this is what a glove box would look like when it's finished, unlike this one, right?
Yes.
Yes, okay.
This is a brand new one. This is one that has been here for almost since the lab started 30 years ago. So it's a lot more filled with different experiments that have grown over time, modifications made to systems as circumstances and use cases have changed. What this box here contains is one of the cleanup parts of our lab. Basically, we have a completely closed infrastructure part. That means all the tritium we use in experiments that might get dirty, in quotation marks, meaning you might gather some hydrocarbon impurities. You use it together with some other gases like helium, for example. This is part of that. Basically, we recover all of that, clean the gas up again, so we can reuse it in later experiments. So we basically don't have any waste tritium that we give off into the surroundings or lose other than through decay. What this part in particular does is a recovery of tritium from tritiated molecules. Basically, if you have tritium incorporated, for example, in methane or other hydrocarbons, you can crack them on catalysts, and if you offer enough hydrogen for exchange, you can shift the equilibrium such that you get the hydrogen onto the hydrocarbons and the tritium into the kind of molecular tritium/hydrogen molecule. And then use that molecule later on to recover from there the isotopically pure tritium, rather than mixtures with hydrogen such as the HT molecule, hydrogen atom, one tritium atom.
So I only know glove box from chemical labs. These look a little bit different. For example, in a chemical lab, these gloves here are pushed to the outside because there's an overpressure inside. Why do those look different?
Those look different right now because they all have these kinds of covers on them on the inside.
Yeah.
Basically, you go through the glove, pick this up, pull it inside this plastic fixture, and then you can turn them to lock them in place. The main idea behind that is if you don't need a glove is just a weak point in your glove box that can damage it easily. It's just thin material. It's thick material, but it's not as thick as a solid piece of polycarbonate. They're also not being blown outward because our boxes are on under pressure. The thought behind that is we want the tritium to be in there and not out where we are. So there's a pressure differential of several millibars to the inside, and that means usually the gloves stick inward and are more difficult to get out of than to get in.
Because you basically want to protect the operator and not a sensitive chemical inside. That's
exactly
basically the difference. Okay.
All of these glove boxes are just for protection of the operator.
Okay.
We do not currently have one in operation that's for protection of a product.
And we were earlier talking about the material these glove boxes are made out of, and
yes.
these gloves here, and also sealing materials. And you said something fascinating about, for example, fluorinated polymers.
Yes. For most chemical applications, fluorinated polymers are great. They're chemically very resistant, but compared to the EV scale of chemical binding energies, the decay energy of tritium with several keV is much higher. So tritium can radioactively break the bonds of fluorinated hydrocarbons and then take that fluorine out of these molecules and form hydrofluoric acid or the tritiated version of that, which means you produce a corrosive acid inside your system that's also radioactive.
While also damaging the polymer, right?
Yeah, you damage the polymer, you produce an acid that then can damage all kinds of other materials, for example, stainless steel, and eat through stainless steel, which is something we don't want, which is why all of our systems contain mostly metal, just pure metal, with some exceptions. For example, ceramic materials are usually something that we can use, glasses. In some limited cases, we can have some other polymers, in particular polymides, which are more resistant, but we still don't want to use them when there's high activities of tritium in the surroundings. And in general, polymers will not survive such an environment for a long time. Okay. And they will not only not survive, they will usually have some negative impacts on the remaining system as well.
But under normal operation, there shouldn't be any free tritium inside this box, right?
Under normal circumstances, all our systems, this is kind of our design guideline, all should be leak tight to basically ultra high vacuum conditions, so less than 10 to the minus 9 millibar liter per second, which means there should not be any tritium getting out of the primary system under normal operating conditions.
So even if you change some connections inside here to change the experimental setup, there also shouldn't be any tritium released, or are there small amounts?
If you open a system, you can never avoid it completely.
Okay.
What we usually do first is we evacuate the system over a long time. We try to purge the system with hydrogen to try to get exchange reactions going to get the tritium off the walls as best as we can. But in the end, you will open a contaminated system to your atmosphere, and usually the moment you open the system, you get some desorption from the surfaces, and that will lead to a tiny bit of contamination getting out.
And what will happen with that air? I see a vent on top here. Where does the air with tritium contamination go, and what does happen with it?
If you just had the glove boxes standing there, the tritium would still over time accumulate inside. So we want to get it out of there. This is the task that's fulfilled by our tritium retention systems. Each box has one, and the entire lab also has one. This is what you can see in our lab as these big yellow cabinets.
Yeah.
Basically, the glove box atmosphere is fed through a catalyst material that turns all manner of hydrogen isotopes, so hydrogen, tritium, into their water form, H2O, HTO, T2O, and that then gets fed through a mold sieve that scatters the water vapor out of the air, and then by that captures the tritium onto it. And after that, the atmosphere goes back into the glove box again.
Ah, so it's basically, it's never vented outside, it's a complete circle.
It's a complete circle. Basically, the mole sieves scatter the hydrogen and tritiated water as water out, and at some point these fill up, and then we can put them in another kind of setup we have to regenerate them, heat them out again, get that water, tritiated water vapor out, and then store it differently. And in that way, we can basically reduce the activity we have inside. So even if you release some, it gets filtered out over time.
What type of vacuum pump is this here? I've never seen one that looks this way.
An issue we have with most of pumps is getting a tritium-compatible pump, so one that has no hydrocarbons inside in any form or manner, is really difficult. Because at some time, for example, a membrane pump has the membrane, a normal scroll pump has at least a tip seal, wet seals. We can't have those. So all of our pumping needs in the higher pressure regime are usually fulfilled by specialized pumps. What we have on the right side is a metal bellows pump. So in the very comically ancient way, you have a bellow that's compressed.
Yeah.
Then you open a valve, let the high pressure side escape, close the valve, extend the bellow again. But in order to safely ensure it, we have like two bellows around each other.
So it's basically a stainless steel bellow inside that basically compresses and expands and thus pumps some medium.
Yes, exactly.
Okay. And what are the seals used in there? Because I mean, I imagine you need some type of seal, right?
It's a kind of thin metal lip that gets pushed open by this cycle.
Ah, okay.
And then seals again. It's not a super tight seal. These pumps leak backwards quite a bit. Okay. So if they're not running. But if they're running, But if you compare this, for example, these pumps can get down to an end pressure of around 60-ish millibars. If you compare that to a normal, nice pump, you can buy a scroll pump, dry scroll pump can get down to 10 to the minus 3 from atmospheric pressure. So we need to pay for our requirements with performance. And that's what the other one is for. That is a scroll pump, but a special one that doesn't have the usual kind of inner structure with the tip seal, but that only does the gas tight sealing by having really, really tight tolerances.
Oh, really?
They are a little bit sensitive to
dirt, I imagine.
Yes, the dirt you can't have, and also accordingly expensive because there's not much use for them outside of kind of very specialized applications. There are really few manufacturers.
What kind of pressures do you reach with those?
You can go to 10 to the minus 3 with that.
Oh, that's amazing.
But you need something like the 60 millibar fore pressure in order to achieve that, which is why we usually have this in combination.
I mean, it's the same problem as with the material for the glove box, that the tritium reacts with so many materials. But how do you do this with all the turbomolecular pumps you're using? I mean, all of them have some type of oil in them.
Yes, turbomolecular pumps are an issue. They do cause your gas to gather impurities. The good thing is they're usually at much, much lower partial pressures. And at those lower partial pressures, it's not as bad.
But I mean, the oil reservoir is at the 4-line pressure, so they're, right? Because the oil reservoir is normally at the lower vacuum side, not the top, the high vacuum side. So it would be...
Yeah, for the small ones I need to show, for the big, I need to look it up. For the big ones we have pumps with magnetic bearings.
Ah, okay.
So there you have some epoxy inside, but you can detect that something's happening. We had extra test experiments exactly to find out, does this work with a turbomolecular pump? How long does the turbomolecular pump survive? This is usually, we have to do some testing to find which devices work for us.
Okay, amazing. How much would you guess does such a pump cost?
Which one?
The left one.
The left one is, I think, something 50 to 80,000.
50 to 80,000, okay.
And the other one is a similar kind of order of magnitude. So yeah, a single pump system already sets us back quite a bit when setting up an experiment.
I think there's probably a reason you never see those on eBay. I mean, I'm looking for vacuum pumps quite a lot. I've never seen one of those.
You can see similar ones to that on eBay.
Yeah, to the right ones.
But this is basically, there's a special variant, this one, that has basically a double contained bellow. So you have the bellow that does the pumping, and another one around, so that if that first one breaks, you're not giving your entire tritium in your system just into the glove box.
Yeah.
And that, I think, more or less adds a zero.
Yeah.
The entire lab has a secondary large tritium recovery system.
This is the central one for the entire lab. So basically, all low activity waste gases that we have get passed through here, and the tritium gets filtered out before we can give waste off through the stack outside of our building into the air. All of that is measured to see how much, if any, we give off into the environment. But so far, we have never given off anything. We always stayed well below the limits that we're allowed to do.
So is this basically the same system used for the glove boxes? So basically molecular sieve, or
molecular
what is in there?
sieves, just in way bigger. Open this up a little bit, and you can have a look inside. And you see kind of, it looks similar to what's in the yellow cabinets. You have mole sieve, you have some catalysts, heat exchangers, cooling.
But what happens to the molecular sieve that has absorbed the radioactive water?
This, for example, is what I mentioned earlier when we were talking about kind of closed cycle and regeneration of our tritium retention system mole sieves. This is the Armor facility where we basically can heat out these mole sieves that you can see one inside a heater jacket, can heat them out and transfer that tritiated water to these collection containers.
Oh, so you basically put the molecular sieve that has absorbed the water that was produced from the glove boxes. You heat them, the water goes through these piping systems here and is condensed into this glass on the bottom here. How much % of the water you desorb there is actually tritiated water? Probably a very small amount, right?
It is a small amount compared to the overall amount of water, just because normal atmospheric air has just so much water in it. That means compared to the tiny leakages of tritium out of our primary systems that are specified to UHV conditions, the glove boxes have much less of a tolerance in terms of leak rate, because it's polycarbonate panels. So you do not get pure T2O, but you do get activities on the order of multiple kilobecquerels per milliliter.
And you said before that tritiated water is a lot more scary than tritium itself. Why is that?
Just because if it's tritium, it's chemically the same as hydrogen. For our biology, the human body doesn't know what to do with hydrogen. It basically does not interact with it. So if you breathe in hydrogen or tritium, you will mostly just breathe it out again. But water, our body knows very well and will readily incorporate everywhere in your body. So if you get it into your body, the tritiated water will stay there for some biological half-life on the order of half a month. And while it's doing that, it's where water is in your body, which is mostly close to your DNA, where it can do damage. So that's why although it does have the same radioactivity, it's chemically much more likely to get into a position in your body where it can do damage.
And that's also the reason all of the people working on these glove boxes have to give urine samples once a month,
basically,
right?
that is why we don't have any dosimeters on us, because external exposure of tritium, the beta radiation of it, will not penetrate even the dead layer of your skin. But if you incorporate it, you have it in your body, and you can't measure it. So you can't measure it with a dosimeter, because it would get stopped just by the housing of the dosimeter. But if you collect human waste, just as with water you take into, that will also get funneled through your system and at some point get out of your body. And then you can take that and do scintillation counting with that to find out how much tritium was in your body in the past month or so.
Okay. And what happens with the tritiated water you collect? Do you do electrolysis to get the tritium back, or is it just stored?
Currently we mostly store it.
Okay.
Ideally, in the future, the thing for the perfect closed cycle is to recover all the tritium back from the tritiated water. So we basically can run our lab completely without producing any tritium waste that we would need to give off at some further point. Part of this big box is one of the core parts of our closed tritium cycle. After we have recovered the tritium in molecular form, so as either T2, DT or HT molecules, we still want to get that tritium back out, because it then is usually mixed up with hydrogen, deuterium, and these other mixtures. We can do this by a process called isotope separation. In our case, we use gas displacement chromatography, which means we have a big column packed with some material, and we push the gas that we want to separate through this material. The tritium and hydrogen and deuterium bind differently with different strength to this material inside, so they different species take longer or shorter when they are pushed through this column, just as in normal chromatography. Which means that once you push this column through, you first get, in our case, tritium out, then deuterium, and then hydrogen. And by doing that, we can get tritium with more than 99% purity out. There's different processes by which you can do this. For example, distillation works as well. But distillation requires a lot more inventory because you need to have a liquid phase.
Yeah.
And that's just some bottom line amount that you need. So this is kind of the most efficient one for our size at the time it was built.
Does the system work on its own? Is it a continuous process, or?
It's a batch-wise process where you have a batch of gas, you push it through as in usual chromatography, and that batch is separated in time.
But do you have to be present, or does it switch between these two columns on its own and does one batch, the other batch, and it's basically a continuous process?
This is manual at the time.
Okay.
We're developing it further as we go along. For example, what we want to do is, for example, I think online monitoring of when exactly do we get tritium out of the column. There we want to go in with some of our newer analytic systems to do real-time measurements of that.
One of the most interesting questions for me was, how do you store a radioactive gas? Storing hydrogen is challenging enough. Hydrogen is a very small molecule and can slip through even the tiniest openings and even diffuse through materials itself. Before we address this question, however, let me tell you about the sponsor of today's video, Radioactive.
In the past, the only affordable option for hobbyists to detect radiation was a Geiger counter. But Radioactive has changed that with its compact scintillation detectors, giving enthusiasts the power of a professional-grade tool at an affordable price. With Radioactive's devices, you're not just measuring radiation, you're analyzing it. The gamma spectrometer lets you identify specific isotopes, like confirming the thorium in welding rods. With their mobile app, you can view dose trends over time, analyze detailed spectra, and store all your data in one place. And those are just a few functions offered by Radioactive. If you're interested in this device, check out the link in the video description.
With that out of the way, let's get back to the question of how do you store a radioactive gas?
This is also one of the core parts of our infrastructure. This is our tritium storage system. Basically, whenever tritium is not in use in experiments where it's mostly handled in gas form, we want to safely enclose that tritium. And the best way to do that safely, and also how we get this delivered to us, is on metal getter beds. The hydrogen or tritium, together with some metals, can form stable metal hydrides that really tightly chemically hold onto the hydrogen and tritium and only release them if you heat them up. So in our case, we do actually have depleted uranium as our getter material, and at room temperature that works as a nice getter pump for tritium and safely absorbs that. But if you heat it up to several hundred degrees centigrade, the tritium can, these metal hydrides dissociate, and the tritium comes out as gas again. And this is what you can have in these beds. Basically, a small container with uranium powder that can be heated.
So in this metal container here, there's uranium powder.
Yes.
Then you push tritium inside. It gets absorbed.
Yes. You don't need to really push it. It will readily get a pump.
Okay. So it will basically pull a vacuum on its own by absorbing the tritium. Okay. And then you can release it again by heating it.
Exactly.
Why are you using uranium? I mean there are hydride storage systems that use palladium. Is it just a flex, or why do you use uranium?
The key word is adsorption isotherm. So basically, at what temperature do you release that again? For most storage systems, you want to not need to expend a lot of energy to get the hydrogen out again. In our case, we want to be really sure that if things fail, if there's a power outage, that the tritium is safely stored inside there and doesn't readily get out just because something happened.
So basically the hydrogen-uranium bond, it's bonded stronger
as a lot of other things you would usually use instead.
Not sure what value you said before. The partial pressure of tritium above the uranium is...
At room temperatures, I think something like 10 to the minus 5.
Okay.
And you can also just repeatedly reuse that a lot.
Do you have many of these storage systems, or is your whole 30 grams of tritium stored in here?
In the default state, when everything is shut down, all up to 40 grams is in this system. We have several of these beds you can see inside here. So several of these beds. You can see on both sides there's a lot.
Oh, yeah.
And if you want to, we can look over there. There's a poster that shows you how they're kind of constructed. A tiny one. Basically, you have the metal hydrate, in this case uranium, in a container with heater wires around it. And through a valve, you can connect it to your gas system. If it's at room temperature, it will start to getter the gas. And if you heat it out, it will start to drive off the hydrogen or tritium again. But since we're at several hundred degrees centigrade, even stainless steel becomes somewhat permeable for tritium. So the tritium will not only take this path out, but it will try to get directly through the container walls.
So it will diffuse through the metal walls here? Okay.
Even if it's a few millimeters thick vacuum vessel, it will diffuse through that.
Ah, so that's the reason for the secondary vacuum on the outside.
Exactly. Just to get any tritium that gets out of there and pump that off as well.
Okay.
Because the outside you can again keep at room temperature. That would just be usually stainless steel.
So if you release the tritium from the uranium storage, how do you get it into the other glove boxes?
Basically, for all of our glove boxes, they are connected. So the system, you can see these two pipes going out of here. These are basically part of the glove box. And inside of these pipes, there's another pipe. It's kind of primary system where the tritium is inside. And from that, you can transfer it to the other experiments in the lab. So all of these glove boxes are at some point kind of connected with that. So you can transport tritium without having to take it into some kind of container, take it out of the glove box, carry it over to the other system, and connect it there again. Okay. This just makes handling, especially of large amounts, a lot safer and easier.
The tritium in this lab is also used for an experiment called Katrin, which aims to determine the mass of the antineutrino. It is a fascinating experiment using a vacuum chamber the size of a building, but unfortunately it is beyond the scope of this video. If you are interested in a separate video about this experiment, let me know in the comments.
A huge thank you to the Tritium Laboratory at the Karlsruhe Institute of Technology, and especially to Alexander, who invited me and took the time to show me around. It's people like him who make these videos possible and give us a glimpse into labs we would otherwise never be able to see. I hope you found this visit as exciting as I did. Other than that, thank you a lot for watching.